My name is Murat Aydemir, and today we will talk about securing our web applications against OWASP top 10 threats in AWS Cloud. Before we dive into today's presentation, let me briefly introduce myself. Once again, my name is Murat Aydemir, and I am working as a Security Delivery Associate Manager at Accenture Prague, Czech Republic, and focusing on both security in the cloud and security of the cloud, basically covering cloud and application security. On the application security side, I focus on dynamic and the static analysis, conducting penetration testing engagements and the red team exercises for the dynamic part, and also performing security-focused or, let's say, offensive source code reviews for the static part. On the cloud security domain, I have been acting as a cloud security architect for last few years, while also contributing to cloud security assessments from time to time, not always, but let's say from time to time. In my free time, I do vulnerability research for mainly web and web-based technologies, and so far I have discovered and reported over 30 CVEs/zero-day vulnerabilities across various vendors, including Dell, SAP, Zoho, ManageEngine, Siemens, Barco, and so on. I am also a huge fan of the serverless concept and the cloud-native solutions. Well, as we go through today's presentation, you will likely notice how much I like the serverless, because most of the architectures we will design and discuss today will revolve around serverless principles. And lastly, I enjoy a lot to reproducing either documented or undocumented end-day security vulnerabilities and perform root cause analysis for them. Frankly, I generally do this certain vendors and their well-known products, which are heavily used by the community, and I generally do this only for high severity or, let's say, niche-ish type of vulnerabilities, such as zero-click RCEs or unusual remote code execution cases, fully account takeover situations, insecure deserialization, and so on. I document and share some of my analysis on my GitHub profile. If this type of works interests you, please feel free to check out my GitHub profile for some of my work. All right, what should you expect from this session today? Well, at first, we will start discussing about security topics in the cloud era. Then I will try to explain OWASP and the OWASP top 10, especially from the penetration tester's point of view. And we will design our core architecture. Afterwards, we will do some architectural exercises to make this solution or architecture more secure and resilient, especially against OWASP top 10 threats. And finally, we will finish up with some detection-based AWS-native defensive strategies. All right. When we talk about application security for cloud-based applications, there are several security topics that come into play, or let's say there are different security understandings as a term. That's why, to ensure we all are at the same page and speaking the same language, I will try to explain some of these security topics. And this will lay a strong foundation for the rest of the session. That's why I would say this part is slightly more important, or let's say the crucial, than the others, especially to having a better view of the whole session, or let's say in general cloud security. Our first security topic is security of the code base. In this security topic, we look for an answer for how can I develop more secure and bug-free codes. As you understand, this area, this topic is nothing but purely at source code level. Our second security topic is security in the cloud. In this topic, we aim to answer a key question, which is, how should I design my cloud-based application in order to minimize the attack surface as well as reduce the number of possible attack vectors? In this domain, we are more into decision boundaries or trust boundaries, data flows, risk assessments, threat modeling, and so on. Actually, it is all about building an application that proactively addresses all security concerns at every stage of the SDLC lifecycle. And our third and last security topic is security of the cloud. In this domain, we are basically focused on building secure, robust, and reliable cloud infrastructures. We are more into data encryption, at rest or in transit, network and perimeter security, identity and access management, logging and monitoring for threat detection, or even logging and monitoring for visibility. Since we want to protect our web applications against OWASP top 10 threats, today our focus area will be security in the cloud. But you will see that while we do this, we will not going to touch the source code or the code base. Instead, we will rely on some cloud-native services, more specifically AWS-native services, to protect our web-based workloads against OWASP top 10 threats. And this approach will allow us to address all possible OWASP top 10 security risks effectively, while also maintaining the integrity of the source code or code base. Okay, now let's talk about OWASP. OWASP stands for Open Worldwide Application Security Project. It is a globally recognized non-profit organization dedicated to improving software security. OWASP operates under open community model, which means anyone can participate in and contribute to OWASP's project. And there are many active projects on the OWASP sites, such as OWASP Cheat Sheet series. This project is a collection of the short guides which designed for mostly either software developers and software architects to help their secure software development lifecycle. And there are plenty different cheat sheets under this project which are focused on different areas and the domains, such as input validation cheat sheet, logging cheat sheet, authentication cheat sheet, session management cheat sheet, secure file upload cheat sheet, and even Docker security cheat sheet. Another promising project from the OWASP side is OWASP AMAS. AMAS is basically attack surface mapping and the asset discovery tool, and it supports both passive and the active recon from many sources, such as public DNS records, public MX records, search engines, APIs, and search engine crawlers. And we generally use it during a recon phase of the penetration testing engagements or red team exercises. We have also OWASP ASVS, or Application Security Verification Standard. It is a framework for the testing the security of the web applications. It provides clear set of the security requirements to help developers, testers, and the security teams to assess their web applications security. And similar to OWASP ASVS, we have also Mobile Application Security Testing Guide. It is a comprehensive resource for the testing the security of the mobile applications. Unlike the ASVS, Mobile Application Security Testing Guide only focus of the mobile applications regardless of the application development platform, either iOS or Android. It also provides step-by-step methodology and the test cases for identifying security vulnerabilities in both iOS and Android applications. I mean, in a nutshell, there are many active projects on the OWASP side, but today our focus area, or let's say our focus project, will be OWASP Top 10. OWASP Top 10, or as known as OWASP Top 10 for web applications. At this point, there might be some misunderstandings because there are other top 10 lists on the OWASP site, such as OWASP Top 10 for API, OWASP Top 10 for mobile applications, OWASP Top 10 for CI/CD pipelines, and even OWASP Top 10 for large language models. But please, every time when I say OWASP Top 10, please interpret as OWASP Top 10 for web applications. The first OWASP Top 10 released in 2003, and the latest one released in 2021, and it was the 7th iteration after the first version was released. But there is a good news, which is they are planning to announce a new release of the OWASP Top 10 in the first half of 2025. OWASP Top 10 is a flagship project of the OWASP and also one of the very first projects from the OWASP side. It just focuses on only security risks, not OWASP Top 10 impacts, not OWASP Top 10 likelihood or vulnerabilities. It just focuses only the security risks. But please keep that in mind. OWASP Top 10 represent literally the bare minimum to cover application security. So what does it mean? It means there are many things to do. There are many best practices to implement for web application security. But once again, OWASP Top 10 represent literally the bare minimum to cover application security. Or you can interpret OWASP Top 10 as a baseline, or I always say that OWASP Top 10 is a must to cover basics and the fundamentals of the application security. Now let's take a look at the OWASP Top 10 categories. And our first category in OWASP Top 10 is broken access control. This category includes security issues like violating the principles of the least privileges, parameter tampering, insecure direct object reference, or either metadata manipulation, and so on. The second category in OWASP Top 10 is cryptographic failures. This category uncovers security issues like unencrypted and plain text communications, use of weak TLS chipper suites, or use of cryptographically weak hashing algorithms such as MD5 or SHA-1, or even use of insecure and outdated padding methods such as PKCS #1 and something similar. Injections rank third in the OWASP Top 10, and I think this category is the most known one among the other categories. This category includes vulnerabilities where user-supplied data is not verified, filtered, or sanitized by the application in a secure manner. And some of the common injections we can mention under this category are like SQL injections, LDAP injections, OS command injections, or expression language injections. The fourth category is insecure design, which refers to flaws in the overall architecture of the application. These issues stem from a lack of security consideration during a design phase of the application, or let's say SDLC lifecycle. To be honest, it is slightly harder to detect insecure design-related vulnerabilities compared to other OWASP Top 10 security risks, because to detect most of the OWASP Top 10 security risks, traditional methods such as dynamic and the static analysis, or let's say the penetration testing engagements and the security-focused source code reviews would be fairly enough. However, and unfortunately, to detect insecure design-related vulnerabilities, we need to conduct proper threat modeling to address these security issues. At number 5, we have security misconfiguration. Security misconfiguration-related vulnerabilities happen when the systems, servers, or the applications are not configured properly in a secure manner. For example, missing appropriate security hardening across any part of the application stack, or improperly configured permissions on the cloud services, enabling unnecessary features on the web server or the web application itself, default accounts, and default credentials. The next category is vulnerable and outdated components. This category highlights the risks of using outdated software libraries, frameworks, or dependencies. For example, use of vulnerable JavaScript libraries on the front end of the web applications, or use of vulnerable and outdated backend frameworks such as Spring, Spring Boot, Fast API, Django, ASP.NET, or .NET Core. Another category in OWASP Top 10 is identification, and authentication failures. This category includes security risks and the vulnerabilities such as missing brute force protection mechanism or the absence of the multi-factor authentications, use of weak or insecure password reset and the forgot password functionalities, passing session identifiers through URL, and so on. Another category is software and data integrity failures. Applications which relies upon plugins, libraries, or modules from untrusted sources, repositories, or the content delivery networks are common issues we can mention under this category. At number 9, we have security logging and monitoring failures. This type of vulnerabilities arise when the application failed to log a critical event or not alert for suspicious activities. For example, missing logs for failed logging attempts within a specific time frame, which we call as a brute force, or not alerting on unusual traffic patterns. Finally, at number 10, we have Server-Side Request Forgery, or SSRF. SSRF is such a vulnerability that allows attackers to force server-side application to make a request to unintended locations. Frankly, SSRF is one of my favorite type of vulnerability, especially when I conducting penetration testing engagements, because once you exploit SSRF successfully, it might give you a lot of useful information for both target application as well as the underlying the infrastructure. All right, that was all about the OWASP Top 10, and now we can focus on our core architecture and the architectural exercises, which we will do pretty soon to protect our web-based workloads. This is our core architecture, and basically we have EC2 instances behind AWS ALB, which are deployed to different availability zones, AZ1 and AZ2. In similar way, we have Amazon RDS database instances for the database layer of the architecture or a solution. And we have completely isolated or separated API that running on AWS Lambda function, which means our API layer is fully serverless, including its associated database. Because as you can see in this slide, we use Amazon DynamoDB as a database layer for the all API operations. Once again, which means once we invoke any of the API methods, it will perform create, read, update, or delete operation on DynamoDB tables. Also, our AWS ALB is public-facing thanks to Internet Gateway attached to relevant Amazon VPC, and we can access our web application backends through associated domain name over Internet. And also, we expose AWS Lambda function, and we can also invoke our API methods over Internet as well. All right, the main question of this session: how can we make this architecture more secure and resilient, especially against OWASP Top 10 threats? To answer this question, from now on, we will review and deep dive some of the AWS services, and the first AWS service we will review is Amazon API Gateway. But first, let's go back to our core architecture for a second. As I said, this architecture works fine with no issue, but there are some challenges of this current design. And basically, we have two main challenges. The first challenge is I need to use two different domains, more specifically two different subdomains to access the same application. Another challenge is I need to handle authentication and authorization at two different places for the same application. Once on the EC2 instances for the web layer, and the second on AWS Lambda function for the RESTful API layer. Well, for the first challenge, you may suggest that use AWS ACM, AWS Certificate Manager service to request public TLS certificate, then verify domain ownership using DNS or email validation. Afterwards, associate this public TLS certificate with both AWS ALB and AWS Lambda function. Yes, you are right, this method works, but also comes with another challenge that we need to solve. And this challenge is, as long as we use the same domain to access this web application and the API, we also route incoming HTTP traffic based on the between EC2 instance workload and the AWS Lambda function workloads. That's why we can simply use Amazon API Gateway for both centralized authentication and the authorization system, as well as the route incoming HTTP traffic based on the URIs. However, to implement Amazon API Gateway into our current solution, we need to do some architectural changes, or let's say improvements, like seen in this slide. This is slightly the same architecture with the previous one, but we have three main differences. The first difference is I just changed the API part from monolithic to microservices, which means from now on, each and every AWS Lambda function represent one individual microservices, or let's say represent one individual API method. The second change or difference is, since we have Amazon API Gateway anymore, our AWS ALB and AWS Lambda functions are not public-facing, but private. And the third and last difference is, since we don't need Internet Gateway anymore, but we have VPC endpoint, more specifically interface type VPC endpoint, to integrate private AWS ALB and Amazon API Gateway service. After doing all of these architectural changes, we successfully implement Amazon API Gateway, and now we can focus on the security features and the functionalities of Amazon API Gateway. All right, let's begin with the most critical aspects of any application security, which are authentication and authorization. Amazon API Gateway offers multiple options for authentication and authorization. It integrates with AWS Identity and Access Management Service, or AWS IAM. This integration allows us to control accesses by using either IAM policies or IAM roles. And this is pretty useful feature, especially if you want to enforce resource-based access control for your web-based workloads running on AWS Cloud. It is also capable to integrate with Amazon Cognito along with Amazon Cognito user pools, which means we can easily handle secure sign-up, sign-in, or the access control mechanisms within the same system. Amazon Cognito handles all of these tasks on behalf of us. And Lambda authorizers. If you need custom authentications, you can use Lambda authorizers by integrating with Amazon API Gateway. For example, if you need verify users through third-party system or a custom logic, you can do it with Lambda authorizers with literally very, very few lines of code. Amazon API Gateway also supports transport layer security, which means all communications between our end users and the Amazon API Gateway can be encrypted in transit thanks to TLS certificates. It also allows us to issue our API keys, and with this feature, we can ensure that only authorized users or systems are allowed to interact with our web application backends, or only authorized users or systems are allowed to invoke our API methods. Throttling and quotas. API Gateway has also a rate limiting feature, and this feature allows us to set how many requests a client can make within a specific time frame. Also, with usage quotas, we can also define or set a number of total requests a client can make over a day, over a week, or even over a month. When it comes to encryption for highly sensitive environments, Amazon API Gateway integrates with Amazon VPC thanks to AWS Private Link Service. This integration is slightly more different than the others. That's why I will not dig deeper into this. But only thing that you need to know about this integration allow us to, or thanks to this integration, we can ensure that traffic stays within AWS network and never passing through or exposed to public internet. And of course, it is also capable to integrate with Amazon Key Management Service, AWS Key Management Service or AWS KMS. And this integration allows us to encrypt sensitive data in transit with managed keys, either AWS managed or customer managed keys. Amazon API Gateway also allow us to set up cross-origin resource sharing policies for our web-based workload. And with coarse policies, we can set or determine which domains or which subdomains are allowed to interact with our web-based workloads. Apart from all of these security features and the functionalities, Amazon API Gateway has also IP whitelisting feature that works at layer 3 networking layer, which means we can easily whitelist our trusted IPs or blacklist untrusted ones. Another question, how can we protect this solution, this architecture, against layer 7 application layer attacks? The answer is nothing but with Web Application Firewall or AWS WAF. With AWS WAF, we can write our own rules to control what kind of traffic we want to allow, what kind of traffic we want to block, or even what kind of traffic we want to monitor. And this could be based on anything from IP addresses to specific HTTP headers, URIs, or even query parameters. But we don't always want to create every rule from scratch, right? That's why AWS WAF also offers AWS managed rule set, which are predefined by AWS to prevent common web-based attacks such as SQL injections, cross-site scripting, file path traversal, insecure deserialization, server-side template injections, and so on. AWS WAF has also bot control feature, and with this feature, we can easily detect and block unwanted and malicious bot traffics while allowing good bots such as search engine crawlers. This feature helps us to reduce unwanted traffic without affecting the legitimate user's experience. It is also capable to control traffic volume via IP rate limiting and the throttling mechanism. This feature is specifically super useful for such a scenarios where implementing CAPTCHA or reCAPTCHA mechanisms are not possible, such as RESTful API like in our case. Geo-restrictions. With AWS Web Application Firewall, we can restrict accesses based on the geolocations thanks to geo-restriction feature. For example, if your business operates only in North America, then you can restrict traffic which coming from the outside of the region or a country thanks to geo-restriction feature. This feature allow us to, or this feature help us to tighten the attack surface of the application as well as reduce the number of possible attack vectors against our web applications. When it comes to logging and monitoring, AWS WAF logs each and every request that is processed. And these logs can be sent to Amazon S3 for the storage purposes, or you can send these logs to Amazon Kinesis for near real-time data processing or near real-time threat detection, or you can send these logs to Amazon CloudWatch to feed your event-driven architectures. Also with Amazon CloudWatch metrics, we can monitor key metrics such as how many requests allowed by AWS WAF or how many requests blocked by AWS WAF. Also allow us to set up alerts based on the unusual traffic patterns or network anomalies. But if you need to implement more complex logic for your web-based workloads running on AWS Cloud, it is not a problem because, as you can see in this slide, AWS WAF is super capable to integrate with other AWS services. Whether you are using Amazon CloudFront to distribute your static contents globally, or application load balancer to distribute traffic to your backend workloads, AWS WAF just sits in front and performs security filtering at layer 7 application layer. All right, another question. How can we protect this solution, this architecture, against layer 3 networking layer, as well as layer 4 transportation layer attacks? With AWS Shield. AWS Shield is a managed DDoS service that comes with two options, Shield Standard and Shield Advanced. While Shield Standard is automatically included at no extra cost and provide basic DDoS protection, today we will focus on AWS Shield Advanced, which provides more comprehensive DDoS protection, real-time insights, and incident response support. AWS Shield Advanced is capable to work at layer 3 networking layer as well as layer 4 transportation layer. And network layer DDoS protection prevents DDoS attacks such as IP spoofing, and transportation layer DDoS protection prevents DDoS attacks such as TCP and UDP float, SYN float, or Smurf attacks. It is also capable to work at layer 7 application layer, and application layer DDoS protection prevents DDoS attacks such as HTTP float or desync attacks. Real-time insights. With AWS Shield Advanced, we get real-time insights via its global threat environment dashboard. This dashboard allows us to monitor all active DDoS attacks across all AWS regions and on all AWS services, giving us a clear view of global threat trends. Beyond DDoS protection, AWS Shield Advanced integrates seamlessly with AWS Web Application Firewall for web application security as well. With AWS Shield Advanced, we get 7/24 access to AWS DDoS response team. This team provides hands-on assistance during DDoS attacks. They help us to analyze the attacks and make mitigation strategies. And the last feature of the AWS Shield Advanced, which is DDoS cause protection. For example, during a DDoS attacks, if your servers scales to handle unexpected traffic due to a DDoS attack, then thanks to DDoS cause protection, AWS will not financially penalize you because of this scaling activity. So what does this mean in real life? All right, it means that AWS will review and evaluate a DDoS attack, or let's say the scaling activity, and if they decide the root cause of the scaling is a DDoS attack, then thanks to DDoS cost protection, AWS will not charge you any money because of this scaling. All right, so far we have talked about Amazon API Gateway for some proactive security controls, also discussed about AWS Web Application Firewall, which provides security filtering at layer 7 application layer, also mentioned about AWS Shield, or more specifically AWS Shield Advanced, to protect our web-based workloads against distributed denial of service attacks at layer 3 networking layer, layer 4 transportation layer, as well as layer 7 application layer. So what about DNS-based attacks? How can we protect this solution against DNS-based attack vectors? The answer is with Amazon Route 53. To mitigate DNS-based attacks such as DNS spoofing or cache poisoning, Amazon Route 53 supports Domain Name System Security Extension, or DNSSEC. DNSSEC adds an additional cryptographic layer onto DNS records and ensures that DNS responses are authentic and have not been tampered data in transit thanks to key signing key and zone signing key. Anycase stripping. Anycase stripping allows each DNS request to be served by the most optimal edge locations, dispersing the network load and reducing the DNS latency, which automatically increase the resilience of the applications against DNS-based distributed denial of service attacks. Route 53 resolver endpoints. Resolver endpoints allow you to forward Route 53 DNS traffic between your on-premises infrastructure and on your Amazon VPC without having to deploy additional DNS server. And we have two types of resolver endpoints, inbound and outbound. Inbound resolver endpoints allow DNS queries and the name resolution to your Amazon VPC from your on-premises network or another Amazon VPC. In similar way, outbound resolver endpoints allow DNS queries and the name resolution from your Amazon VPC to your on-premises network or another Amazon VPC. And by using these resolver endpoints, we can ensure that Route 53 DNS traffic between AWS cloud and on your on-premises network is secured all the time. Shuffle sharding for fault isolation. If any DNS server, or let's say any DNS worker node, fails somehow, the other DNS worker node on Amazon Route 53 notation we call as a DNS shard, the other DNS shard can be absorbed the remaining workload. So let's say one of our DNS shard hit by a DDoS attack or experience misconfiguration. In a typical shared environment, this situation could affect many customers, right? But thanks to shuffle sharding, only the users which connected to specific shard is affected. The rest of the users with their own unique shard configurations remain unaffected. It's a little bit complicated algorithm under the hood, but only thing that you need to know about shuffle sharding is it allows us to fault isolation, more specifically DNS-based fault isolations during traffic spikes or distributed denial of service attacks. Geo-proximity routing policies. Imagine that we are running globally distributed application across multiple regions and in multi-AZ setups, right? This feature allows us to manage and restrict Route 53 DNS traffic to our resources based on the geolocations thanks to geo-proximity routing policies. To be honest, this feature does not affect the security directly, but it helps to increase the resilience of the application which globally distributed. Amazon Route 53, of course, integrates with AWS Shield seamlessly to fan out DNS traffic to many endpoints or many edge locations in case of distributed denial of service attacks. What about safer content delivery and securing our static contents? How can we handle these two topics in AWS? We can use Amazon CloudFront service to handle secure static content delivery. Well, every time when I ask what is Amazon CloudFront, more or less I always got the same response, which is Amazon CloudFront is a content delivery network of AWS Cloud. Yes, I can say that the answer is partially correct, but I can also say that Amazon CloudFront is literally much more than content delivery network. Geo-restrictions. When we talk about Amazon Route 53 a little while ago, we said that we can manage and restrict DNS-based Route 53 traffic to our resources based on the geolocations, right? Thanks to geo-proximity routing policies. Now with Amazon CloudFront, we are able to restrict any kind of traffic, not DNS-based ones, to our resources for both static contents such as CSS files, JavaScript, images, and everything, as well as for dynamic contents such as server-generated response or API response. I mean, with Route 53, we were only able to manage and restrict DNS-based traffics. Now with Amazon CloudFront, we are able to restrict any kind of traffics, both static and the dynamic contents as well. Amazon CloudFront supports HTTP over TLS or HTTPS, and this means we can all communication between Amazon CloudFront edge locations and our end users can be encrypted in transit thanks to TLS certificate. Field level encryption. Field level encryption allows us to encrypt sensitive data field in the HTTP post request before they reach out to our backend servers. This feature, field level encryption, generally used by payment gateways or in banking industry in order to encrypt credit card or other PII informations rather than encrypting the entire HTTP request body. With Amazon CloudFront, we can restrict access to S3 bucket objects thanks to Origin Access Control feature. Origin Access Control prevents unauthorized accesses by bypassing Amazon CloudFront and accessing S3 bucket objects directly. In similar way with Amazon CloudFront, we can also restrict access to our static contents thanks to sign URL and sign cookies. These two methods, sign URL and sign cookies, give us a control over who can access our static contents and for how long. We can specify expiration times, we can restrict access to certain IP ranges, or even we can restrict access to specific AWS credentials. Origin Shield. Origin Shield, which acts as an additional caching layer between Amazon CloudFront edge locations and our origin servers. It helps us to reduce the network load on our origin servers during traffic spikes or distributed denial of service attacks. All right, another question. How can we handle secure authentication and authorization? Actually, when we were talking about Amazon API Gateway, we partially mentioned about these two topics, authentication and authorization. But in AWS, we have dedicated service to handle secure authentication and authorization, and this service is Amazon Cognito. With Amazon Cognito, we can easily set up secure sign-in, secure sign-up, and the access control mechanisms for our web applications, backends, mobile applications, or APIs. And it supports various kind of authentication mechanisms, including multi-factor authentications, password policies, and even federated accesses from third-party identity providers such as OpenID Connect, OAuth 2.0, and SAML. When it comes to logging and monitoring, with AWS CloudTrail, we can capture Amazon Cognito API calls. Then either you can use these API call logs to, or you can send these API call logs to your third-party SIEM product, or you can send these logs to Amazon S3 to perform your own security analysis by running SQL queries thanks to Amazon Athena. Also with Amazon CloudWatch metrics, we can monitor, report, and take automated actions in case of events in near real time. And lastly, with Amazon CloudWatch Log Insights, we can configure AWS CloudTrail to send events to Amazon CloudWatch for monitoring Amazon Cognito AWS CloudTrail log files. I know it's a bit complicated, that's why I will reply once again, I will say once again. With Amazon CloudWatch log insights, we can configure AWS CloudTrail to send events to Amazon CloudWatch log files for monitoring Amazon Cognito CloudTrail log files. Now let's take a look at the sign-in example with Amazon Cognito, how it works under the hood. In the first step, a client provides credentials to Amazon Cognito. In the second step, Amazon Cognito, along with Amazon Cognito user pool, tries to validate user-supplied credentials, right? If Amazon Cognito validates user-supplied credentials, it returns temporary security token or ID token to the client. In the first step, client make an API call over HTTPS with this token. In the next step, when this API call hit to Amazon API Gateway communicates with Amazon Cognito in order to validate this ID token or temporary security token. In the fifth and last step, if Amazon Cognito verify this ID token, it redirects users to default page or the landing page and assign valid session cookies or JSON Web Token. It really depends on what kind of session mechanism in place. Let's say if it's mobile application, it will redirect users to default page and assign JSON Web Token, which is more common to use in the mobile application. Or let's say if it's web application, it will redirect users to default post login page and assign valid session cookie if the web application use cookies to manage user identities. What about our security sensitives and secrets? How can we handle secrets management in AWS? Today, we will use and implement AWS Secrets Manager servers to handle handling our security sensitives and the secrets, but actually we have one more option in AWS to handle secrets management in a secure manner, and this service is AWS SSM Parameter Store. But since AWS Secrets Manager offers more comprehensive security features and the functionalities compared to AWS SSM Parameter Store, today we will only focus on the AWS Secrets Manager. Okay, let's assume that we have AWS Lambda function that is responsible for authentication, right? Okay, let's say /API/authenticate API endpoint. For this purpose, this API method needs to validate user-supplied credentials by connecting to credentials tables in Amazon DynamoDB. But the point is, we don't want to store our Amazon DynamoDB credentials into AWS Lambda function as hard-coded or plain text. Yes, we can set Amazon DynamoDB credentials as an environment variable of the AWS Lambda function. We can do it, AWS offer this, but this approach will not solve our problems fully because this approach does not provide enough security for all possible attack vectors for security sensitives and secrets. That's why at this point we can simply use AWS Secrets Manager to solve this challenge. But also, as you can see in this slide, we also need to attach execution roles onto AWS Lambda functions to retrieve secrets from AWS Secrets Manager. Now, let's take a look at the content of the execution role. Then afterwards, we can deep dive the security features of the AWS Secrets Manager. When you attach execution role to AWS Lambda functions, more or less it will look like this. It's similar to IAM policies or IAM roles. But the question is, how should we read this execution role, right? Now, let's try to read this execution role together. This execution role allows relevant actions on this resource. Once again, this execution role retrieve the secrets in US East 1 region under associated account ID. And the name of the secret we want to retrieve is uppercase secrets underscore name. Encryptions of secrets. Before they are saved, all secrets stored in AWS Secrets Manager are automatically encrypted at rest using AWS Key Management Service or AWS KMS. This means even if someone gains unauthorized access to our secrets stored in AWS Secrets Manager, they wouldn't be able to read it without proper decryption keys. Automated secret rotations. AWS Secrets Manager takes care of secret rotation for us. It rotates secrets automatically without causing any downtimes or service interruptions, which is super helpful for site reliability engineers or, let's say, in general, platform engineers. Tracking secret accesses. AWS Secrets Manager integrates seamlessly with AWS CloudTrail, or in other words, with AWS CloudTrail, we can capture AWS Secrets Manager's API calls. Or this means that we can easily track each and every interactions with our secrets thanks to AWS CloudTrail. Who accessed or modified a secret, what secret was accessed, when it happened, and from where. All these informations can be tracked thanks to AWS CloudTrail. This is going to be the last question from my side. Can we fit everything on one slide? Well, if we try to fit everything on one slide, our final architecture will look like this. And now let's take a look at our final architecture. As we spoke before, we use AWS Lambda functions to build our RESTful APIs, which means our RESTful API layer is fully serverless. Also, we store our data in Amazon DynamoDB, which is also serverless, and we don't worry about the infrastructure maintenance, operating system updates, scaling or provisioning capacity. We also use and implement Amazon API Gateway that also scales automatically and route incoming traffic based on the routing policies. We use AWS Web Application Firewall, provides protection or prevents common web-based attacks at layer 7 application layer. Also, we implement AWS Shield, more specifically AWS Shield Advanced, which provides DDoS protection at layer 3 networking layer, layer 4 transportation layer, as well as layer 7 application layer. And we also use Amazon CloudFront to distribute our static contents globally. Also, we use Amazon Route 53 for DNSSEC, NICS stripping, and the shuffle sharding, and as well as the geo-proximity routing policies. And lastly, we use Amazon Cognito for secure authentication and authorization. And sorry, for the last one was the AWS Secrets Manager to handle secrets management for our case. Yes, my session ends here. I know I exceed my time, but since we don't have any other session after this one, I think it wouldn't lead any problem. Thank you everyone for coming here. Thank you for joining.